Welcome to the memory address decode video. I've redone this a couple of times now, and I'm going to try something a little different this time, see how well this works. Let's introduce this example chip here. I have a little chip drawn, and it has one line on it that will be a chip enable. So I've labeled it with the word enable, just to remind us what that function is. So one of these pins, these little legs sticking out the side here, each of these are an input or an output. Sometimes they can be both, but that's what their function is to move data in and or out of a chip. And so an enable would be an input into the chip where we turn the chip on or turn it off. Technically what's happening is we'll cause it to disconnect from the bus or reconnect from the bus. So in one of the diagrams we saw, that was the timing diagram, the address bus was shown to be in a high impedance state. It's at high Z, and high impedance meant that the chip was basically it was disconnected from the bus. It was not a 0 voltage or a 1 voltage state. It was just completely disconnected. So just imagine that we have a lamp that's plugged, that's plugged into the wall. Okay, it may still have a voltage there. It may be a ground voltage there. I turn it on and the current flows. I can unplug the lamp and it's completely disconnected from the power. So that's a third state. So sometimes people will talk about tri-state logic. That's an example of that. It's not important for our class here, but I think it is important to understand the memory disconnect, because we need to be able to turn things on and turn things off. And the reason is that we need to avoid ambiguity. When we address something out on the computer, we can't have 3 or 4 things answer to us, because we'll get crosstalk. If I ask a question in class, I need one person to answer, not 5 simultaneously, because I wouldn't understand any of what was being said then. Okay, so we have to address individual things out there, just like we might address a package to a particular house, or I might call on a particular student in class. We want to communicate with one entity at a time, and so the enable will be how we signal the chip that we want to talk to it. So we will enable it to talk to it, then disable it, and it will ignore everything except for the enable line. All right, now this particular chip is going to be for my little example, it's going to be a 4-bit by 1 DRAM. So let me just label this. Okay, so that nomenclature 4 by 1 means that there are 4 bits in it organized 1 bit wide. So think of this as a matrix, and the first number is going to be how high it is, and the second number is going to be how wide it is. Let me draw that for you. Okay, so this shows us with some sample data. Okay, I just put 4 bits of data in here at random. Okay, we see that it is 1 wide, 4 tall, and at any particular time we can ask for one of these by position. Okay, so we could ask, give me value 0, give me first value 1, value 2, value 3. They will be numbered starting at 0, going up to the last. Very much like an array index. So let me just show you what I mean by that. And down here I have some sample code that one might write to declare an array that now has 4 values in it, and I have set one of the values to true as an experiment here. Now in our programming language we probably wouldn't set it as a 1, because most languages don't view that, they view Boolean values as being solely true and false, but let's just pretend. Okay, so we're just pretending here, and that would set one of these values to 1. Now, I haven't described how they're numbered here, but let's talk about that little part right there. How do we address individual bits within a chip? We will have to give each one of these an address. That will be a binary value. We'll count it from 0, 1, 2, 3, just like we would give these array indices 0, 1, 2, 3. Okay, so let me bring over the address that corresponds to these values. Okay, so I shoved my data over a little bit to make room for the address. Note that I've expressed the address as a 2-column value there, because there's 2 digits in the address. Since there are 4 values there, numbered 0, 1, 2, 3, if I write those indices out in binary, they would be 0, 0, 0, 1, 1, 0, 1, 1. I need 2 digits for this. So our first observation is how many address lines do I need to come into this chip? Each address line can hold 1 bit of an address. So I will need 2 address lines coming into this chip to hold that address. Now, the chip manufacturer will tell me what the address lines are. They will label all of the pins. When I buy this chip, I'll get a piece of paper that lists what all the pins are here. I don't get to pick them arbitrarily here, but here I'm just coloring in, saying, let's pretend that this is what the manufacturer told me that my address lines are going to be these first, pins 2 and 3. Well, I guess we'll start number at 0. Would be enable pins 1 and 2 will be the 2 address lines. Okay, so my address was going to be a binary number put on those lines. And that just means I'm going to put a 0 on this line or a 1 on this line. So we can take a wire and we can put a 1 on it by putting a high voltage on it, or a 0 on it by putting a lower voltage on it. And that's how we'll signal our values there. You don't have to think about voltages if you don't want to. If you're comfortable with just this idea of we're going to put a 1 on that pin or a 0 on that pin. Now, if I want to get the very first value out, I put 0, 0 on these 2 pins, and out comes my first value. If I want the next one, I put 0, 1. Okay, so one of these bits is going to be a high order pin bit, and the other was going to be the low order bit, and that will be given to us by the manufacturer. If you go look at the that 62256 chip that I had in one of the slides, you can see that it listed a bunch of pins as A0, A1, A2, A3. Those are the address lines. Okay, and there was their chip enable was like, I think they called their chip select, so it was called CS/CS for an active low. Okay, so what we've all right, so the capacity of the chip, 4 bits, told me that it had to have 2 bits for the address, because I knew I had to number my values from 0 up to that. So if I have 4 bits, it will go up to 0 to 4. If I had 5 bits, it'd be 0 to 3 for 4 bits. If I had 5 bits, it goes 0 to 4. But memory is typically done in powers of 2. For reasons that will be clear as we go along here. We want to be able to fully decode and use the entire address lines that were put in here. So I don't want addresses left over, so it's uneconomical. So my next largest RAM would be an 8-bit RAM, and so I would, of course, need 3 bits then, because I'd need to have values going from 0, 0, 0 to 1, 1, 1. Okay, those are the that's 7 up there. That's 0 through 7, my 8 values. If I add 16 bits in there, 0, 0, 0, 0 to 1, 1, 1, 1. All right, so we know how many bits there are by the capacity, because I would know how do I write the largest number in binary. Now, if you're still uncomfortable working with binary, you need to practice that. We're not using terribly large numbers here. We're not using anything that you can't work with. You shouldn't be able to work with easily. But you should practice that, and you should also note that powers of 2 only have a single bit on there. A power 2 minus 1 is going to have all of its bits turned on. So 8 is a power of 2. 7 is the one value below it, so it's 3 ones. 16 is a power of 2, 15 is the one below it, 15 is all ones turned on. Okay, so we can see that pattern going forward there. So you should be able to be comfortable working, very comfortable working with values below 16, and still be able to work with these values for powers of 2. I'd say up to 256. You probably should know those. So practice those, write them down, you can't take 10 minutes to do a conversion on something like this on an exam. I'm not going to allow you that much time. You need to have that skill practiced. So just like learning any other skill, sometimes you just need to drill on it a bit. Okay, but we're working with small numbers here, and this should go pretty quickly there. I know, based on the size of my memory, when someone told me it's 4 bits long, that it has to have 4 discrete values there. I'll need 4 discrete addresses for those values, and they will be starting at 0 always, going 0, 1, 2, and 3. Okay, and I also know, since I practice my binary, that in order to get up to 3, I'll need 2 bits. Okay, if I go to 4, that's going to push me into a 3rd bit, and I need to have a 3 address lines. And 3 bits on my address line would take me from 4 all the way up to 7, and then at that point I'd have to go into a 4th address line, because 8 is 1000, and that would take me all the way up to 15. Okay, so that range of how many address lines covers how many bits is an important skill that we're going to need to work on here. Okay, so I drew those address lines and extended them out from the chip a little bit, just so I had a little bit of room to work with. But let me draw in the address bus. The address bus are going to be the lines that are connected up to the processor, and it will also connect everything connected to that address bus, meaning all of the memory chips will connect up to it, and any other devices that need to connect into that memory bus. So if I had other devices I needed to talk to, like a video chip or any peripheral you might want to think of, I'm going to have to talk to it somehow, and the most common way of doing that is to talk to it through the memory bus by what we call memory mapping. So we will give it a location on in the address space, and we do that by wiring it to the address line. So let me draw some address lines in. I know I need at least 2. Okay, so I've drawn in 2 of these address lines here. I should label these so that we know which ones are which. Okay, so I've labeled one of them A0 and the other is A1. A stands for address, so that separate from other lines that are out there, and they will need to connect into the address lines on the chip. Now, just because I have an A0 and an A1 in my system address line doesn't mean that it connects into the A0 and A1 on the memory chip. It depends on where I locate them. But that's something we're going to do in this exercise here. But we will start that with this first stage of the description here. Right now, I have made no connections. It's important that we draw our lines that we don't. I mean, they're going to have to cross each other like they did right in here. And so, if you see those lines crossing, we assume no connection between them. Okay, that they just crossed each other. If we need a connection, we need to actually draw in some sort of a dot. So let me draw those, connect those address lines in. Okay, so I've slightly exaggerated these dots, but I wanted them to be visible. So here we have 2 big dots here that are placed on the intersection of 2 lines where they crossed. If you see a dot, or if you make a dot, this means that the A0 connects to the top of my red address lines, and A1 connects to the lower one there. So okay, so now I've wired this chip in, and its addresses are at the low order of the address range there. Now I may have more address lines than I'm using just for this purpose. So let me draw a couple of more address lines in. Okay, so I've drawn in a couple more. These blue lines are system address lines. Okay, so a system address bus. At no time have I ever asked how long does the system address be, although we can make some assumptions from our problem that it has to be at least so big. So the only thing we know, if I'm using 4-bit tall DRAM, if it's 4 bits by some number like 1 here, I know that I'm going to need 2 address lines to address those 4 bits. So I must have at least 2 address lines on the system, or else I wouldn't be able to use all of this memory. I may have far more, and that's not important right now, just which ones do I use, but I can at least determine a minimum number. Okay, so we've introduced this idea of a chip and how it connects into the address bus and how the addresses work like array indices to tell us where something is located. The next thing I think I want to talk about is that memory is addressed in bytes at a time, not by bits. We don't wire in a single bit to the address bus because everything on the system is going to need to have 1 or more bytes coming in to work with it. So our memories have always been organized 8 bits wide, so I'm going to need to have 8 of these chips. So let me do a little reorganization here to get to my 8 bits. Okay, I have now made 8 of these chips here, removing a little label here, and I need to hook up these address lines, but you note that in order to show this, these 2 address lines need to connect into the pins on each one of these chips. So I'm going to need to do that separately here. So I've moved the chips down a little bit so you can see these connections. Okay, I think we've shown what's going on here. It took me a while to draw in here. But now each of the 8 chips in this bank, this collectively is being known as a bank of memory, is now wired into A0 and A1. All 8 of them respond to the same address. Now, you might say that's a problem because I don't want 8 devices to respond to the same address, because I just kind of made that point earlier. But in this case, each one of these is going to give me 1 bit out, because it's 4 by 1 DRAM, as we labeled one of these. So collectively, they're going to give me 8 different bytes, 1 from each of their spots there. So that means then that each one will give me a separate bit. Collectively, they form a byte. So that means my bank is good. While my chip might give me bit 0, bit 1, bit 2, bit 3, my bank is going to give me byte 0, byte 1, byte 2, byte 3. And that byte will be made up of 8 separate bits, 1 of those bits from each chip. Okay, so this is how we address this in here. Now I've placed this using address lines A0 and A1. That means that if I put a number on the address bus, as you can see, I have 4 address lines up there right now, so I can put any number from 0 to 15. Any of the numbers on this bus over here from 0 to 3 will refer to this bank of memory. Okay, I could move this bank of memory to a different address just by wiring into different address lines. If I, instead of wiring it into A0 and A1, if I wired it into A1 and A2, then I would be just using these 2 middle lines of the address there. And so if anything that had a the 0001, 1011 of these 2 lines would activate this bank. Okay, so if I put in, for example, a 1010 in that case there, if I were to put that on that address line, and if I had banks 2 and 1 wired in, I'd be using these middle 2 digits there, and that would mean value 1 that I wanted out of that array. Okay, so the address that a chip responds to, the index of it, may not be the same number as we put up here. It may be part of that number. Now we tend to make things easy on ourselves by having the memory adjacent to each other and then starting at some low value. Maybe not 0. Maybe, I think the Intel chips, for example, the Pentium chips, they start their memory at 128K. I mean, the first 128,000 entries in the address space are not connected to memory. And then memory begins after that. And that's not something that you see as a programmer. that's handled for you by the tools that you use. They automatically move things around to fit them in. But if we're studying the architecture, we'd have to understand that where we put things in, where things are placed in memory, is solely a function of how they're wired into the address bus. So we could wire this bank in to any two of the 4 address lines, and we can get wildly different addresses that it responds to. It's possible we could even have them overlap another bank. That would be a disaster, and so we try to avoid doing that. We want to make them adjacent to each other. Now, so if I added another bank of memory in here, what I would do is just copy this bank and bring it down and just wire it into 2 different address lines. So let me try doing that. Okay, I've doubled the memory on my system here. I've made a second bank of memory. Notice they're wired into the same address lines. This is something I said, I wanted to avoid doing. But how in the world am I supposed to get the addresses to appear as the values 0 through 3 if I don't use these 2 lower address lines? The way I'm going to solve this problem is by using the chip enable. I have not wired that in yet, but I will continue to allow them all to share their same addresses within this range, 0 through 3. Both banks will get those addresses coming in from A0 and A1. Okay, so they both get those. But what I want to do now is I want to select this bank. I'll call this first thing bank 0 and this lower one bank 1. I want to turn this bank on independently of this bank. And I don't want them to be on at the same time. So what I'm going to do is I'm going to use a third address line. I'll take address 2 and use it for this purpose. Okay, address 2 by itself will give me 2 different values. So this is where I talked about the dual roles of bits in the address. Some bits, like address 0 and address 1, are used to tell me where something is within a chip or within a bank. Okay, they give me the values 0 through 3. And then now, if I'm going to have more than one bank, I'm going to have to identify the bank. And if I bank 0 and 1, I can do that with 1 bit. Okay, that bit will be 0, means I'll talk to the upper bank. If the bit is 1, I'll talk to the lower bank. And so I can do that with address 2. And I'll just wire that into the chip enable. So let me pause and do that. Okay, I've connected the top line in with the top purple line connects into the chip enable. So whenever A2 is turned on, that top bank will turn on. The bottom bank I haven't hooked up there because it's like if I do the same thing, I'll turn the second bank on at the same time. I only want one of them to come on at the same time. And now in reality, I should say chip enable is usually active low. So an active low line means now that if this thing is ever 0, this turns on, which is what I want. So this is the correct decoding for an active low chip select. If I want to do the same thing down here, I'll need to turn this on when this is 0. Okay, because when this line becomes 0, when this line becomes 1, I'll need to turn it into a 0. And so I'll need to put an inverter in. I don't think I have a handy inverter here, but I'll go. Well, actually, I think I do have one. So let me go and get one of those and wire it in really quickly, and then we'll wire the second piece in. Okay, hopefully you can see. Okay, I just added an inverter in here. And now, when this address line turns on, when that becomes a 1, this will turn into a 0 and bring this and then activate those chip selects. When this address line is a 1, it deactivates these because these are active low enables. If this address line is a 0, these turn on. If this address line is a 0 here, this will go through the inverter, become a 1, and turn these off. Okay, because once again, these enables are active low. That's what I assumed here. So here we've fully we've done a full decode of both these banks. and we can see how we've arranged so that only one bank at a time can turn on. Now, if I had more banks than this, or if my if I had more banks than this, I wouldn't be able to use a simple inverter. Here, by only having 2 banks, I need 2 values to select my my bank. So I'm using, I'll use 1 or more address lines just to do bank select here. In this case, I'm using just 1 line, A2, for this purpose, and so I can just wire it in with an inverter. If I have 4 banks, I would need to have 2 address lines. And now I wouldn't be able to do this little inverter trick here. I'd actually have to do the same thing we did when we did in combinational logic, when I gave you a truth table and I said, come up with a circuit that turns on when this value is true. Well, what is the circuit that would turn on when we saw a particular pattern? If I had 2 address lines I was using, say I was using A2 and A3 to address 4 banks there, I'd have 0, 0. Well, that would turn on the first bank. How do I do that? Well, I'd have to run those through an AND gate to see if they're both turned on, and I can negate them to see if they're both turned off. Now I probably want to use a NAND gate here. With a negated AND, because I want my output to be inverted. I want the gate to be on, to be off when both of my inputs are selected. In other words, I want to invert the output, just like I inverted here. I would invert my NAND and not just a regular signal there. So I would, if I had a 1 1, or let's just do 1 0. Let's say I wanted to, I have 4 banks and I want to decode bank 2. Well, let's see. First of all, let's give me a circuit that turns on when I see a 1 0 there. So a 1 on one line and a 0 on another. What I do is I'd invert this line here. So this would go through an inverter. Okay, well, I'm not going to draw that. And then this line here would not go through an inverter. These two would both go into an AND gate. And so that 0 becomes a 1. And I see 1 1 as the inputs into the AND gate. Anytime 1 0 were the inputs into this little circuit I'm building. Okay, so that would turn on when we saw that. But since I have an active low gate select, or chip select, I'll want to invert that again. So what I'll do is, instead of running it into an AND gate, I'll run it into a negated AND, a NAND gate, and that will give me my 0 output whenever I see a 1 or a 0 coming in. Okay, and so I could do the same trick with a 0 1. I'll just flip these 2 rows around. 0 0 would have both inverted. 1 1 would have neither of them inverted. And you can do the same. You can generalize that to however wide your bus needs to be. Okay, if I have 8 banks, then I'll need more address lines. 16 banks, more address lines, and so I'll just have more lines being used just to select the bank. So some of my address lines are being used to select the value within the chip. Okay, so that's a dual role that I talked about. Here, in this particular case, we're using 2 address lines to select the 4 values within the chip. Some of the address lines are being used to select the bank. Here I'm using 1 address line to select between 2 banks. Okay, you can use this, so you could do the same thing with bigger chips. You'll just need more address lines to select values within the chip. And you can use more banks, you'll just need more address lines to select within the bank. Okay, so that is going to be left as an exercise to you. I just wanted to introduce the concepts here with this example here. Now, let's go over the types of things you're going to need to do on a worksheet here. The questions that you were asked before, and you're going to be asked to do it again, the same questions. First, it says, So in my new worksheet here, we're going to be using 32 by 1 DRAM. Okay, so let me just write that down here. It's 32 by 1. That means think of that array as having 32 elements in it. Okay, 32 elements in it there. Is it different than a 4-element chip? Yeah, it's just bigger, but it'll operate just the same. It will have chip selects on each for each of those chips. We will need to have 8 of them to make a byte. So a bank will be 8 wide. That's not going to change. It's just that there will be more bytes in a bank. Instead of having 4 bytes in a bank, we'll have 32 bytes in a bank. So that's nice. It gives us more memory. So first question, how many addresses does a single chip have? That's a question here. So in this case, how many addresses does a single chip have? It has 4 addresses because I have 4 pieces in it. What is the range in addresses in binary within a chip? That's kind of like this little chart that or table that I built that had, I'm trying to see if I can drag it back over here, but it's not, it is not cooperating with me. This thing right here showed the addresses for a 4-bit chip, 4 by 1. Okay. Now I don't need you to draw out every single one. I asked for the range of them. What is the smallest value within the largest value within a particular chip? So, once you've told me how many addresses you're going to have, you're going to have to number them. So one hint is you'll always start numbering at 0. So that's the small value of the range. You'll just need to tell me what the upper value of the range is, and you'll need to give me the range in binary, because we are going to need to know how many bits wide that value is, because that's the next question. How many bits are required to express an address within a chip? Well, here, how many bits are needed to express an address within one of these chips? Well, I have my values range from 00 to 11. Those were the address ranges there, 0 through 3 for my 4 elements there. So I needed 2 bits for that. That 2 bits correspond to the 2 address lines I'm using down here, and they're being wired into 2 address pins on the chip. Okay, so we're getting a little ahead of myself here, but first question though is to recognize how many bits does an address require. Okay, and that's solely a function of how big the chip is, what the capacity of the chip is. Okay, a 4-element chip required 2 address lines because we needed 2 bits to address those. If I had a 2-bit memory, I could get by with 1 address line, 0 or 1. It would tell me which bit I was asking for. Okay. So how many bits are required to express an address in a chip? Well, if you've given me the address range above, you just take the largest address, the last value there, and count how many bits did you need to express that number, and that's your answer. Okay, next question. How many address pins will our chip need to have? Well, that's really is how many of these little red lines am I going to need to have going into the chip. As you can see, it's the same number as the number of address lines, because each one of these pins will wire into an address line. Okay, the next question is, it says, well, what if we doubled the size of the memory, which I did right here? How many system address lines are required to access that much memory? Well, all right, let me look at, I don't think I exactly answered that for this question here. If I have one bank of memory of my 4 by 1, I have 4 bytes. If I added a second bank, I now have 8 bytes total. How many discrete addresses do I have for the whole memory as a whole? I have 8 addresses. 4 for the first one and 4 for the second bank. Okay, how many address lines do I need to come up with 8 discrete value? I need 3. And indeed, you can see I have 3 address lines being used here, A0, A1, A2. Okay, I need all those address lines to give me 8 different values here. 4 for the first one, 4 for the second one. Okay, so the question is, how many address lines are required, that much memory there? Once again, think about what's the range of system addresses you're going to need for all of your memory. For here, if I have 8 bytes of memory, my system addresses will be 0, 0, 0 to 111. Okay, there will be 0 through 7 of them. Obviously, no single chip can handle that type of an addresses. My single chips only take 4 bits. Only have 4 bits. So they wouldn't know what to do with a 5, 6, or a 7 coming in, or even a 4 for that matter, because they take it in as a binary number. 0 through 3 is the only thing they understand for these particular chips. They only have 4 values that are stored. They only have 4 indices, and they only have 2 address lines for us to indicate those addresses. But when I start building multiple banks out of there, I am now going to need to create addresses that are larger than any single chip can use. Specifically, in this case, I needed to create addresses 4, 5, 6, and 7. No chip can understand those, but what I did was I gave both banks access to the first 4 addresses. Both banks see it as 0 through 3. It's just that whether it's a 4, 5, 6, and 7, what's different between 4, 5, 6, 7 and 0, 1, 2, 3? It's this third bit. Okay, when the upper bank turns on, or I should say when the high order bank turns on, bank 1 in this case, its addresses will be the same 0 through 3, but it will have an upper bit set on that, 4, 5, 6, 7. So write out the numbers 0 through 8 in binary. There's only 8 values to do, so that won't take you long. So if you're not seeing this 100% solid there, write those out in a column and in binary there. So it'd just be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 110, 111. Okay, there they are right there. That's how long that took to do this thing there. And we see that the first 4 addresses in there, I'm looking for my cursor to see what happened to it. There they are. So the first 4 addresses all have a 0 in their first column. Otherwise, they count 0 through 3. The second bank here has a 1 in that first column, but otherwise has 0 through 3 down here in the low order bits. And so we recognize that pattern there, and we take this third bit here, this high order bit, and we use it as a bank select to select between bank 0 and bank 1. And you can tell that the low order bits are perfectly suited to tell me what the offset is within a bank. Now I kind of did the work that I just asked you to do, so maybe you might want to do it from 0 through 16 and see how that would work with 4 banks there. 4 banks of 4, and you'll see that you'll need to have 2 bits to indicate the bank, because I have 4 banks now, 4 banks of 4. And so see how those upper 2 bits will give you a binary number 0, 1, 2, 3 for the bank number, and the lower order bits are perfectly duplicating that 0 through 3, 0 through 3, 0 through 3. Okay, this is also one reason why we make our banks of memory powers of 2 in size, so that so we can exploit these patterns in the binary numbers. We want everything to be multiples of 2, so that they can use so many digits for this and so many digits for that. It's not a whole lot different than if we were doing this in base 10 and we said we want our numbers to be divisible by multiples of 10. All right, so then if I did that, I might have so many digits used for this task, and then so many digits to tell me the bank number. Okay, it works out just fine in base 10 as well as base 2. It's just that when we're doing these type of memory addressing, we will use it in base 2 because that's what our values are. Okay, so the question 3: how many system addresses are required to access the larger thing of memory, and how many system address lines are required to access that much memory? The same thing as asking you is how many digits will there be in a binary number that will be for the largest address in your chunk of memory. So if I have 64 bytes of memory, I will need to know how many bits I need to represent not 64, because my numbers will not go from up to 64, they'll go up to 63. If I have 128, bytes of memory, you'll need to go from 0 to 127. So I'll just say how many digits would I need to express the number 127. All right. Now, and you know, you can use a calculator for this this worksheet. That's okay. On an exam, I wouldn't let you use the calculator. I'd either give you a problem that's so small that you should be familiar with the numbers, you know, like 0 through 16, or I might give you some of a table or some reference where you could look it up as just an extra sheet of paper. That's a better thing to do for me, because I won't want you to be able to, you know, be able to use a calculator to perform the base conversions and tasks you're supposed to do. But when it comes to just looking up and seeing patterns like this, you should be able to do that for small values easily, either in your head or just pencil and paper without very much time. And if they get larger values, just having the table already done for you, you can just look up what you need. Okay, next question. Next question we'll ask. We noticed that we need to use a larger address for the system that a single chip can address. So in this case here, we needed 8 system addresses to hold 8 bytes of memory, but our banks each hold 4 bytes each. So a bank only needed 2 binary digits to represent its address, 0 through 3, 0 through 3 down here. They're the same 0 through 3. They're wired into the same 2 address lines down here. Okay, so we know that the system, though, needed to have extra bits there, specifically 1. And so the question would be is how many bits would you allocate each of these 2 duties? One duty is to come up with an offset within a chip or within the bank, if we're looking at it as a byte-oriented thing. And so here I said, well, I have 4 bytes in my bank, or 4 bits in my individual chip. Those are both true statements there. In each case, I need 2 address lines to form an address 0 through 3. So I know that 2 of my address lines are going to be used for that purpose there. Second duty is to say how many banks do I have. I need to be able to identify the bank number with my address. Here I have 2 banks, so I can do it with a single address line added onto that. So there would be 1 address line for that duty. Now, if I have 4 banks, I'll need to have 2 address lines for that. And I'd have 2 for the bank and 2 for the offset within the bank, giving me a total of 4 address lines. And so if I wanted to build a 16-byte memory, I would take 4 4-byte memories and add them together, doubling what you see on the screen right here. And I would need to put in 1 more address line because I just doubled it. Every time I double my memory, I add 1 more address line. So that's a true statement as well. So it says the sum of my answers here should equal the answer to the previous question. So the previous question was how many system address lines do I need? I need 3 to give me values 0 through 8. The sum of my answer here, well, I need 2 of these blue dots and 1 of these black dots. That's 3. 2 plus 1 is 3. They equal. All right. And then the last question is asking to draw 2 circuits here. Now the worksheet you are going to get are going to use bigger chips, so that might seem like more work, but it really isn't too much more work, because the only difference is that if I ask you to do a larger chip here, well, if I ask you to do a larger chip, let me just pick a somewhat larger chip and not quite the size you're going to use, and you'll see that isn't too much more work there. If I doubled the size of the chip from 4 bytes to 8 bytes, I would need to have 3 address lines going into it. Okay, because 8 bytes requires addresses 0 through 7. The largest number is 7, which is 111. 3 bits there. All right, so if I double the size of that, all it made me do is just add 1 more address line in here. It's the same type of a drawing, but I just pulled 1 more down for those. The question is showing you, is saying draw that decode, and that means a decode circuit means I want to show the address lines, the system address lines, and how they're wired into the chips. There will be connections needed for the offset into the chip, these blue dots, and their connections. And then this purple line for the chip select will need to be somehow calculated. Now, once again, this is a deceptively simple drawing right here, not because of the size of their chip. It won't matter. It's the number of banks that are going to matter. But you will be asked to, first of all, do a 2-bank solution, and you'll be asked to do both of those banks so that you can show me. Otherwise, there's a trivial solution to each of those problems there, and it doesn't really tell me anything. If you do the trivial solution, you still might not understand this. If you do 2 banks, you'll have to do at least one of them non-trivially. All right, so I did 2 banks of the 2-bank problem here, but let's say I had 4 banks. Now I would need to have 2 address lines for the bank number, okay? Because if I have 4 banks, the banks are going to be bank 0, bank 1, bank 2, bank 3. That requires 4 discrete values, or since I number them 0 through 3, they will require 2 digits out of the address to identify the bank. So that means now I'm going to need to use some AND gates and some inverters to identify the bank number. Okay, so you're going to be doing just the same thing you did for combinational logic when you said, I want the equation to be true if this is pattern is seen, or if this pattern is seen, if this pattern is seen, is this pattern seen. So it's just like sum of products. It's just like sum of products, except that you only have one function, one value that's going to be true going in your sum of products. So you can leave out the sum, because it's just an OR gate connecting all the things together. Well, if you only have one thing going into that OR gate, the OR gate's not needed. Okay, so I think I've explained all of the questions here, and I think I've also given you a video here that shows how to do the circuit there. So I'm going to post the worksheet on Sakai, and I'm going to get this video encoded and up to YouTube. I'll email that out to you, and then this will be due sometime next week. It won't be due the first class session. It will be due the second class session of the week. That way you have time to ask some questions about it, and and if by some chance you don't check your email until the start of the week, you shouldn't be. But if that's the case, then you still have time to work on that. But I did tell you that I would be redoing this assignment. At least I told the Thursday class on that, and so we will. So get back to me with any questions you have on that. Let me just get this encoded for you.